Welcome back, focused learners. Today we've got a genuinely fascinating explainer lined up for you. We're taking a deep dive into the biochemistry of insulin resistance. Specifically, we're looking at how a very specific natural compound, fermented pollen, works right at the cellular level to regulate glucose. If you've ever wondered how just biotransforming a natural food can turn it into a wildly potent metabolic tool, you are absolutely in the right place. Okay, let's dive into this.
So here's our roadmap for today. We're going to start with glucose absorption, then move on to GLP-1 hormones, look into SCOBY fermentation, compare Amrita against natural bee bread, and finally, we'll wrap up with the super intriguing AA7 peptide hypothesis. Let's get right into it. Section 1, Glucose Absorption, SGLT1, and GLUT2. We're starting this journey all the way down at the cellular level, specifically looking at CACO2 enterocytes. These are basically our gold standard lab models for human intestinal cells.
To really understand how fermented pollen impacts us, we first have to understand the baseline mechanics of how our gut actually absorbs glucose. Now, think of SGLT1 as this incredibly diligent, active pump. It literally sits right there on the surface of your gut cells and uses sodium to actively pull glucose in, even when it has to fight against the gradient. But, it has a limit. It absolutely can get saturated. On the flip side, we have GLUT2. Picture GLUT2 as your body's emergency overflow valve. Normally, it just hangs out at the bottom of the cell, moving glucose out into your bloodstream. But when you have a massive spike in glucose, say after eating a really heavy meal, GLUT2 rapidly inserts itself right into the top membrane to act as a passive, high-capacity absorption channel. It's wild. This is actually why certain drugs that only block SGLT1 don't stop all glucose absorption. That GLUT2 overflow valve just kicks right in.
Moving right along to Section 2, GLP-1 and the hormonal response. We're talking about a massive cellular domino effect here. Because, those transporters we just talked about, they don't just absorb fuel. They actually act as the main trigger for a massive systemic hormonal cascade. Let's break down the logic step by step, because it brilliantly illustrates our enteroendocrine response. Step 1, sodium and glucose rush into the cell through that SGLT1 pump. Step 2, this influx actually changes the cell's electrical charge, a process called depolarization. Step 3, that electrical shift pops the calcium channels wide open, flooding the cell with calcium ions. And finally, Step 4, that calcium is the trigger. It tells the specialized L cells and K cells in your gut to release metabolic hormones, GLP-1 and GIP, straight into your bloodstream. So literally, the very act of absorbing glucose is what tells your body to prepare the insulin response to handle it. Actually, before we move on, there's this really fascinating little physiological nuance I want to highlight. While this whole glucose influx heavily stimulates intestinal glucagon-like peptides like glycine and GLP-1, it simultaneously inhibits your traditional pancreatic glucagon. It is just a beautifully calibrated system, right? The gut is essentially shouting, hey, prepare for incoming energy, while the pancreas is getting the memo to stop releasing its stored sugar. Okay, Section 3, matrix transformation, specifically SCOBY fermentation. Let's explore pollen's molecular evolution. So, having established our cellular baseline, how does turning raw bee pollen into a fermented superfood change the metabolic equation? Well, raw bee pollen is already fantastic. It naturally inhibits the enzymes that break down carbs, which slows down glucose absorption. But a recent 2024 metabolomic study using liver cells, HepG2 cells to be specific, proved that fermented pollen is on a whole other level. It's vastly superior. See, fermentation doesn't just preserve the pollen. It promotes significantly higher glucose consumption by the cells and ramps up glycogen synthesis. How? By actively flipping the switch on the PI3K/AKT signaling pathway, which is pretty much your body's master switch for insulin sensitivity. And as if that wasn't enough, the fermentation process unlocks brand new hypoglycemic phenolic compounds that just aren't bioavailable in raw pollen.
The real magic behind why this happens comes down to a term called free aglycones. You see, in raw pollen, a lot of the really beneficial antioxidants are locked up tight. They're trapped in these complex sugar bonds, or glycosidic bonds. But when you introduce a SCOBY, that's a symbiotic culture of bacteria and yeast, those tiny microorganisms act like microscopic scissors. They enzymatically hydrolyze, or, snip those bonds apart. This releases the free aglycones, things like quercetin and gallic acid, making them highly bioavailable for your body to actually use. This specific hydrolytic unlocking process is exactly why SCOBY fermentation yields such incredible antioxidant capacity and fights insulin resistance so effectively.
Moving on to Section 4, Amrita versus natural bee bread. Let's talk about why standardization is absolutely crucial.
It is time for a bit of a commercial reality check here. We need to compare human-engineered SCOBY fermentation, which you'll often see commercially as the Amrita complex, against natural bee bread that's just made by bees in the hive. When you put them side by side, the differences are pretty stark. Raw pollen, low bioavailability, and a really variable profile. Now, natural bee bread is genuinely fantastic. It goes through the spontaneous lactic acid fermentation right in the hive, which gives it high bioavailability. But, and this is a big but, its batch standardization is basically non-existent. And the microbial profile? Totally uncontrolled, because it completely depends on whatever random microbes happen to be hanging out in that specific hive. Fermented pollen like Amrita, though, kind of gives you the best of both worlds. You get very high bioavailability, but because it uses a strictly defined SCOBY consortium in a controlled lab setting, you get completely predictable batch-to-batch standardization. And look, if you're going to use a compound for targeted clinical applications, you absolutely need that predictability.
Finally, Section 5, the AA7 peptide hypothesis. We are literally stepping onto the absolute frontier of diabetic research right now.
And this brings us to a really provocative question. Can a naturally biotransformed compound like fermented pollen actually mimic the pharmacological effects of modern anti-diabetic drugs? No way, right? Well, let's look at the data.
So in a recent study, researchers zeroed in on a newly identified peptide called AA7. Now, this peptide is derived from a specific protein, adenylate cyclase, that the honeybee naturally adds to the pollen. But here is the absolute game changer. AA7 acts as a natural DPP4 inhibitor. For those who might not be super familiar with the terminology, DPP4 is basically the enzyme in your body that destroys the GLP-1 hormone. In fact, a lot of modern diabetes drugs, known as gliptins, work exactly by inhibiting DPP4. And AA7 does this naturally. By slowing down the breakdown of GLP-1, it massively amplifies your body's natural insulin response. Plus, it locally modulates those exact SGLT1 and GLUT2 transporters we talked about earlier in this explainer, right down there at the gut level. Now, as focused learners, we do have to practice some cautious scientific optimism here. There is a catch. In the study, this AA7 peptide was generated through simulated human digestion using lab enzymes, not through actual SCOBY fermentation. However, the prevailing hypothesis here is incredibly strong. We know SCOBY contains a rich matrix of proteases, which are basically protein-snipping enzymes, so it is highly plausible that during the Amrita fermentation process, the SCOBY consortium cleaves that exact same bee protein in a very similar way, meaning it could be naturally generating the AA7 peptide before you even consume it. And that brings us to our final thought today. As the researchers themselves state, SCOBY fermentation might generate peptides with a profile similar to AA7, but rigorous analytical validation is the next required step. And honestly, that's just the continuous, beautiful process of scientific discovery, isn't it? We've seen how fermentation drastically unlocks pollen's molecular potential, how it shifts glucose transporter dynamics, and powers those vital PI3K/AKT signaling pathways. Now, the potential that it's also acting as a natural gliptin drug, that opens up an entirely new world of research. Will the upcoming mass spectrometry tests prove this groundbreaking hypothesis? I don't know about you, but I am absolutely thrilled to find out. Thank you so much for joining me on this explainer. Keep asking those great questions and keep learning.